All right, we're doing this example of an optimization problem where we have an open box. I'll pull the previous page back for a moment. We have an open box with a square base, and we're assuming that this box has a fixed surface area of 108 square inches. And so what we've done is we've come up with a primary equation, which is the volume as a function of both x and h, the width and the height. And then we took a secondary equation, which basically expresses that constraint of surface area has to be 108, and then used that to solve for one of the variables, h, and make a substitution, which eliminated the h and gave us a function of x only. Okay, so this is what you need to be able to do. You have to have both. In many problems, you have to have a primary and a secondary equation in order to eliminate one of their variables and get down to a function of a single variable. Then I explained how we're going to have a realistic domain of x values from 0 to the square root of 108. So I've just written down what we've got so far. We have our volume function, volume of the box as a function of the width x, and then the domain of that function that we're working with. So now we can kind of forget about the whole box scenario and forget about everything else and just treat this as a problem where we're trying to find the maximum value on a closed interval. So we can just apply the closed interval method we learned back in section 4.1. First, we're going to need to find critical numbers. So let's take a derivative of this volume function. Derivative of v prime of x. It's going to have a 1/4 because that's a constant multiple. And then the derivative of this polynomial in here, we can just apply the power rule to each term and get 108 minus 3x squared. Okay, so critical numbers. Well, first of all, it's never going to be undefined, so we don't have to worry about that. And then it's going to be 0 when what? Well, the 1/4 is never going to be 0. If we set this all equal to 0, what would have to happen is 108 minus 3x squared would have to equal 0. Well, that means the 108, well, let's write it this way. The 3x squared has to equal 108, right? Those two terms have to equal each other so that they cancel each other out to give me 0, right? So 3x squared has to equal 108, and then if you divide both sides by 3, we get x squared equals 36. So that means x would be plus or minus 6. There's two solutions to that equation. Now, plus or minus 6, the only one of those two critical numbers that is actually in our domain is the positive 6. Okay, so only x equals 6 is in the domain 0 to the square root of 108. So that's our only critical number we have to worry about. And if you think about the context again, I know we said we don't have to think about that at this point, because at this point you can just be on, sort of autonomous mode and you're just like doing the math, right? You don't even necessarily have to be thinking about the box right now. But if you do take a moment and think back to the fact that this is a box, negative 6 wouldn't make any sense, right? Because x is a real world length. So there we go. So x equals 6, and then the closed interval method just says test the function v at that number as well as the endpoints. So we're going to do v of 0, v of 6, and v of the square root of 108. Okay, and let's see, v of 0, the volume when x equals 0 is going to be, we're going to have x equals 0 here and x equals 0 here. That's going to be 0 in both cases. And v of 108, by the way, the square root of 108 rather, when you stick in the square root of 108 for x, you will find that also equals 0. Okay, and just for a moment, I want to bring back this picture and point out that with these extreme situations I was drawing pictures of here, as x approaches 0, the volume of this gigantic tall skyscraper box is going to also approach 0 because it's this very, very skinny long thing. It's like having a line. It's going to approach 0 volume. And then in the other extreme case, when h approaches 0 and you have this very shallow wide tray, that volume also approaches 0. So yeah, the endpoints of our domain have output values of 0, And the critical number in the middle, x equals, well, not the exact middle, but it's near the middle, x equals 6. This gives me an output of 108. So stick that back into the volume function here, and you will find it equals 108. So that means that is our max volume. So we can sum up the problem by saying the max volume is 108 cubic inches, okay? Because it's a volume, so cubic inches. And that occurs when x equals 6 inches. So we want to have a box with a 6-inch base, 6-inch by 6-inch base. And then the height would have to be given by this equation here. We can stick 6 back in here. We need this to be equal to 108 surface area, right? So you could stick 6 in there. I have to do this in my head. I'm going to pull out the calculator for this part. I'm going to do 108 minus 6 squared, and then all divided by 4 times 6. And that is 3. So it occurs when x equals 6 and h equals 3. So we have a 6 by 6 base with a height of 3. So that means for an open box, you can generalize this and say, well, what we found here is that the width here is exactly twice the height. Okay, so this is like, if this is h, this would be 2h, right? The width is exactly twice the height. If you have an open box with a square base, the maximum volume you're going to get out of that is when it's twice as wide as it is tall, okay? That's what we found here, and if we had done this in generality, we would have discovered this relationship of 2 to 1 between the dimensions here. So yeah, I think that's a pretty cool problem. This is only our first example of an optimization problem. In the next video, I'm going to walk you through kind of a step-by-step approach that you can use for optimization problems, kind of like dreads for related rates. I've made up my own kind of dreads equivalent sort of thing for that, and then I'm going to show you several more examples.